Imagine descending through black water so deep that sunlight no longer behaves like light, only like memory. Your instruments hum, the hull creaks, the beam from the submersible reaches forward and seems to strike nothing at all, until the darkness begins to shimmer, not with one monster, not with one glowing eye, but with an army. Thousands upon thousands of tiny living sparks, each no bigger than your hand, each carrying its own pattern of cold blue light. This is lanternfish, Myctophidae, not a single species, but a vast family of around 250 species spread across roughly 3 dozen genera, among the most abundant and widespread fishes in the deep ocean. In some estimates, they make up about 60% of deep-sea fish biomass, a number so large it stops sounding biological and starts sounding geological. Long before scientists truly understood them, lanternfish had already tricked human beings on a planetary scale. During World War II, sonar operators began seeing what looked like a second seafloor hanging hundreds of meters above the real one. Stranger still, this ghostly bottom moved. By day, it sank. By night, it rose. For a while, the ocean seemed to be lying. Later, researchers realized the floor was alive, a dense layer of fish, squid, jellyfish, and other mid-water animals reflecting sound back to ships. Lanternfish were a major part of that illusion. In other words, one of the first great modern encounters with this animal was not visual at all. It was a military misunderstanding of life so numerous it impersonated geology. To sonar crews, lanternfish were not fish. They were a phantom continent. Their world is the Mesopelagic, the ocean twilight zone, usually from about 200 to 1,000 meters deep. It is not the deepest part of the sea, but it is one of the strangest. There is not enough sunlight there for photosynthesis. Day and night still matter, but only barely, as faint differences in dimness. Temperatures hover near freezing in many regions. Pressure can climb toward roughly 1,500 pounds per square inch. The water column feels empty, yet it is packed with lives adapted to near invisibility. Gelatinous chains, silver needles, drifting traps, soft-bodied predators, and fish that glow like coded messages. Hoy describes this zone as holding more fish than the rest of the ocean combined. It is a place where life survives, not by dominating the environment, but by negotiating with it second by second, by becoming dimmer, quieter, lighter, faster, softer, and harder to find. Lanternfish themselves do not look like the gigantic nightmares of popular deep-sea fiction. That is exactly what makes them unsettling. Most are small, often only a few inches long, though some species reach larger sizes. They are usually dark, silvery black or smoky bronze, with oversized eyes, narrow bodies, delicate fins, and rows of photophores, tiny light-producing organs set along the head, belly, and flanks. In many species, those photophores are not random dots. They are elaborate anatomical devices built from photosites, pigment, reflectors, and modified scale cups, almost like miniature lanterns assembled inside the skin. From a distance, the fish can look like a sewing needle threaded with blue fire. Up close, it feels more uncanny, a creature shaped by darkness until nearly every part of it seems optimized either to gather the faintest light or to manipulate it. That light is not decorative. It is language, camouflage, and survival technology. Lanternfish eyes are tuned to a dim blue-green universe. Studies show many species absorb light in the range, most useful for detecting bioluminescent signals, and some theoretical models suggest they may detect such signals from as far as 30 meters under ideal conditions. Their large eyes, reflective tissues, and special gaps in the eye structure help them capture the little light available. Their belly photophores can help erase their silhouette from predators below through counter-illumination, while the lateral patterns may serve as a form of species recognition, an elegant solution in an open ocean where mates are scarce, and the wrong encounter can mean wasted energy or death. Scientists have even compared this kind of signaling, half-jokingly, to a matchmaking system in the dark. And then there is the movement. Lanternfish live inside one of the largest daily migrations on Earth. All over the planet, every night, enormous numbers of midwater animals rise toward the surface to feed, then sink again by dawn into deeper, darker safety. Hawaii calls it a massive living wave. Australian researchers studying spawning schools in the Coral Sea described lanternfish ascending after sunset from daytime depths of roughly 400 to 1,000 meters into the upper 200 meters, where food is more available. Imagine that scale. Billions of small bodies climbing through black water in synchronized hunger, then vanishing again with the sunrise. A forest cannot do this. A city cannot do this. Only the ocean can turn migration into weather. Lanternfish do not simply inhabit the Twilight Zone. Every night they remake it. What are they climbing for? Mostly prey small enough to miss until it is too late. Copepods, euphorsiids, pteropods, salps, appendicularians, hydrosans, and other zooplankton. Traditional stomach studies long suggested crustaceans such as copepods and krill-like euphorsiids were their main diet. But newer DNA-based work has shown something richer and stranger. Some lanternfish also consume substantial amounts of gelatinous prey, soft-bodied animals that older techniques often missed because they digest too quickly to leave obvious remains. That means lanternfish are not merely chasing crustaceans through the dark. They are woven into a broader, more flexible food web than scientists once realized. They hunt what the Twilight Zone offers, and that flexibility matters. In the abyssal dark, specialization can be power, but opportunism can be immortality. Their story reaches far back into Earth history. The earliest unambiguous fossil lanternfish are known from the late Paleocene and early Eocene, meaning this lineage was already present not long after the catastrophe that ended the age of non-avian dinosaurs. Paleontological work suggests early myctophids were not yet fully committed to the high oceanic lifestyle of their modern descendants. They likely lived more over shelves and upper slopes during the Eocene, then expanded more decisively into deeper oceanic settings later, especially by the Oligocene, when their remains become increasingly prominent in deeper marine sediments. That timeline matters because it means lanternfish did not simply appear as the deep ocean we know today. They moved into it, adapted to it, and eventually came to dominate it. Their rise was not a single invention. It was a long negotiation with a changing planet. So why did they survive while so many other lineages vanished or dwindled? No study can give one final cinematic answer. But the evidence suggests a powerful combination of traits. Lanternfish are globally distributed, extraordinarily species-rich, and often capable of wide vertical movements through changing light, temperature, and pressure regimes. Their diversification appears to have kept increasing over time, rather than hitting a clear evolutionary ceiling. And because the open ocean lacks the obvious physical barriers seen on land, researchers think their diversification may have been driven not only by geography, but by ecological gradients, oceanographic fronts, and perhaps the visual signaling built into their photophore patterns. That is my informed theory of their endurance. Lanternfish survived because they were not built for one place. They were built for transition, for edges, gradients, movement, and change. In a world repeatedly reshaped by climate and circulation, that may be the most durable design of all. Even their buoyancy hints at that flexibility. Many mesopelagic fishes use swim bladders to manage life in the water column, but in some lanternfish species, the gas-filled swim bladder regresses with age, while lipids take on more of the buoyancy role. Researchers have suggested this shift may reduce the physiological constraints imposed by gas at depth and allow more extensive vertical migration in adults. In plain language, some lanternfish may become better deep commuters by carrying less internal gas and relying more on oils and soft tissue chemistry. That makes sense in an environment where pressure punishes every pocket of air. The lanternfish body is not armored against the deep the way a submarine is. It is negotiated into the deep, lightweight, flexible, chemically tuned, almost like a thought that learned how to swim. Reproduction in a place like this should be nearly impossible. The open mid-water has no reef, no cave, no nest, no coastline, no obvious meeting point. And yet lanternfish solved the problem well enough to become one of the most successful fish families on the planet. Their species-specific light patterns may help them distinguish one another in the darkness, reducing the chaos of finding the right mate in a vast three-dimensional void. In the Coral Sea, Australian scientists documented large schools of spawning lanternfish for the first time in Australian waters, confirming that under the right conditions, these otherwise elusive fishes can gather in remarkable density. When they do, the rest of the ocean notices. Tuna slash through the schools. Whale sharks, billfish and seabirds join the feeding frenzy. A lanternfish aggregation is not just a reproductive event. It is an alarm bell rung through the food web. Modern scientists are still trying to catch up with an animal this numerous and this elusive. Nets alone do not tell the whole story. Today, expeditions combine acoustics, cameras, irradiant sensors, and environmental DNA. NOAA's deep-sea system was built to map deep scattering layers across large areas of the water column while imaging the animals within them. UHOI's Ocean Twilight Zone project has used ships, moorings, and missions, such as exports, to study how mid-water life behaves and how much biomass different ocean structures can hold. In warm core eddies, for example, WHOI reported as much as 5 times more animal biomass than outside those features. That means lanternfish do not just live in the twilight zone uniformly like dust in a basement. They gather in patterns shaped by moving physics, eddies, fronts, temperatures, oxygen, and currents. To understand them, scientists must track not just fish, but the architecture of invisible water itself. And still, the fish keep surprising us. In 2026, researchers studying deep-sea fish larvae reported that lanternfish larvae, such as Benthosema terratum, possess unusual hybrid photoreceptors. Cells that look rod-like in shape, but use cone-like molecular machinery. As the fish mature, they shift toward true rod-dominated vision, suited for darker depths. This matters because it suggests lanternfish do not just inherit a deep-sea eye, they grow into one. Their vision changes with the light environment of their life stages. Most marine fish larvae live in bright, shallow waters, but deep-sea fish larvae can inhabit dimmer, gloomier settings, and their eyes appear adapted for exactly that in-between world. So even before a lanternfish fully descends into the deep, its body is already rehearsing for darkness. Evolution did not simply give it better eyes. Evolution gave it a developmental pathway that treats twilight itself as a habitat worth designing for. This is one reason lanternfish matter so much to modern science. They are not just prey, they are infrastructure. Every night, by rising to feed near the surface and returning downward, lanternfish and other twilight zone animals move carbon through the ocean. They eat carbon-rich prey produced ultimately from surface photosynthesis, then transport that material deeper through respiration, waste, and their own bodies. WHOI describes the twilight zone as a major part of the biological pump that helps move carbon away from the atmosphere and into the deep ocean. Studies on myctophids show this transport is real, even if its exact magnitude varies by region. In the North Atlantic ridge, their active transport was estimated as up to 8% of sinking particulate organic carbon. In the Southern Ocean, myctophid respiration contributes substantially to total mesopelagic fish carbon processing. In other words, this little glowing fish is part of the machinery that helps regulate climate. That same importance makes lanternfish politically and economically dangerous. Because they are so abundant, some governments and industries see them as a potential fishery resource for fish meal and aquaculture. But researchers are increasingly warning that harvesting mesopelagic fish could ripple upward into predator populations and outward into biogeochemical cycles. HOI has highlighted the risk that expanding fishing in the Twilight Zone could deplete a critical food source for tuna, swordfish, and other species. Modeling studies in the North Atlantic suggest exploiting mesopelagic fish communities could alter both trophic interactions and carbon export. The challenge is brutal. How do you extract value from one of the largest moving biomasses on Earth without damaging a food web we still barely understand? In the deep sea, abundance is not permission. Sometimes abundance is a warning label, and even without a massive new fishery, the modern ocean is already reaching them. A 2025 study using museum specimens found microplastics in 55% of 1,167 lanternfish examined, with contamination increasing over time. By the latest period studied, roughly 2/3 carried at least one particle. The deepest oceanic dramas often seem timeless, but they are no longer untouched. The lanternfish's ancient commute now intersects with our synthetic debris, a creature shaped across tens of millions of years to read faint blue light and survive crushing darkness, is now swallowing fragments of packaging, fibers, and industrial residue. There is something especially tragic about that. Not because lanternfish are cute or famous or easy to anthropomorphize, but because they are fundamental. When a foundational animal starts filling with our waste, the whole ocean begins speaking back. Still, for all the data, mystery remains everywhere. Scientists do not yet know the true global biomass with confidence. They are still debating how much carbon mesopelagic fish move, how resilient lanternfish communities will be under warming and deoxygenation, and how exactly this family became so diverse in an ocean with few hard barriers. Some evidence points toward ecological divergence across water masses and light environments, some toward the role of photophore signals, some toward oceanographic structures acting like invisible borders. The open sea looks uniform to us from above, but lanternfish reveal that it is partitioned by gradients we cannot see: temperature edges, oxygen deserts, current systems, polar fronts, and private languages of light. That may be the deepest lesson they offer. The ocean is not empty because we cannot read it. It is crowded with meanings we are only beginning to decode. So when people ask whether lanternfish are terrifying, the honest answer is not in the way they expect. They are not terrifying because one might attack you. They are terrifying because they force you to confront scale of darkness, scale of adaptation, scale of time, scale of hidden labor. While continents argued, empires fell, and human history flickered across shorelines, lanternfish kept rising and sinking through the midnight water, carrying carbon, feeding predators, exchanging coded light, multiplying into hundreds of species, and impersonating the seafloor itself. They are a reminder that some of the most powerful animals on Earth are not the largest, loudest, or most visible. Some are tiny, cold blue, and almost impossible to hold in the mind. And maybe that is the perfect ending, because lanternfish are not really an ending at all. They are a threshold creature, a fish of the almost seen, a pulse inside the planet's circulatory system, a survivor from ancient oceans that learned not to conquer the dark, but to speak its language. If you could follow a lanternfish down on its final descent before dawn, past the fading surface glow, past the last silver flashes of prey, into the black pressure-loaded quiet where the world narrows to heartbeat and bioluminescence, you would not feel like you were watching something primitive. You would feel like you were watching a masterpiece of adaptation, still in motion. And then, just before it vanished, you might understand the most unsettling truth of all. The deep sea is not silent because nothing is there. It is silent because life there has become too refined for noise. Lanternfish are proof that in the darkest part of the living ocean, survival does not shout. It glows,